Today we are here to introduce Elevator Express. This is a program that allows building developers to determine the number of elevators needed for a building. It also helps to determine the optimal behavior of the elevator system. Now before we dive in, let's introduce the team. We are all students at the University of California, Berkeley studying operations research.
Hi, I'm Taylor, and I'll be talking about the value that Elevator Express can bring to your elevator system.
I'm Anirudh, and I'll be providing a brief description of how the simulation model behind the program works.
I'm Keenu, and I will be discussing what assumptions we make about the elevator system and how we can adjust the program for our client-specific needs.
I'm Emily, and I will be giving a demonstration of how to use the program's interface.
And I'm Danny, and I'll explain how to interpret the program's output.
So, why would you want to use this program? Did you know that in the past year, New York City office workers have cumulatively spent 16 years waiting for elevators? Time spent waiting for elevators represents a huge loss of productivity. Minimizing elevator waiting times reduces that waste, while also improving overall employee experience. Here are some of the questions that our program answers, which help users decide how to build and operate their elevator systems. Before construction, you might want to know how many elevators should be installed in a building, given you want to satisfy a specific service level. For an existing building with elevators already installed, first question you might ask is, what is your elevator passenger's current expected waiting time? Second, at which floor should an elevator wait if it's not operating in order to minimize passenger waiting times? And finally, how will upgrading current elevator system to a faster speed affect passenger waiting times?
Now I'd like to help explain the model behind this program. At the start of the simulation, customers will arrive according to a non-homogeneous Poisson process throughout the day. Once a passenger arrives at the floor, the system will find the first available elevator. Then it will send that elevator to pick up the passenger, or multiple passengers if there are more people waiting. The passengers then enter the elevator and start moving up to the next floor, where it is decided how many passengers will get off. When the elevator stops, this passenger will get off the elevator. This causes the elevator to become idle, and it will move back to its idle position. Finally, we check if there are more passengers waiting, and if there are, the process starts once again. Here's a detailed run-through of our model. While the animation showed the basics of what our model is capable of, this graph shows the full details of the logic used to simulate the elevators.
In our program, we make a few assumptions to make the model we use more realistic and or simple. In regards to how passengers riding the elevators behave, we assume that 1. The in-arrival times of the passengers can be described by a non-homogeneous Poisson distribution. 2. The floor at which passengers want to get off can be described by a beta distribution. And 3. Passengers are either headed up or headed down. In other words, the elevator does not accommodate double-riding passengers that choose to go down a few floors in order to go up. Using a homogeneous Poisson distribution to simulate passengers' inter-arrival times is particularly salient because Poisson distributions can reasonably approximate how passengers arrive in real life. Additionally, it makes sense to use a non-homogeneous Poisson distribution because we realize that the average passenger arrival rate varies over time. In regards to how the elevators themselves behave, we assume that 1. The service times for the elevators are deterministic. That is, there exists an algorithm or an equation to determine how long it takes passengers to reach their given floors. 2. The elevator's capacity is in terms of passengers instead of total weight. This implies that all passengers have a uniform weight. And 3. All the elevators work perfectly all the time. The elevators never break down, and there are no issues that would prevent the elevators from working.
While those are all our current assumptions, we would like to expand our model's capabilities based on our client's specific needs. Ways to do this include modeling varied floor capacity, elevator breakdowns, and zoning behavior. Now let me take you through this simple user-friendly interface. Enter in your elevator specification. Say you have around 10 floors and you want to test out a range of the number of elevators, say from 1 through 10. Then you can also change the travel time between the floors, setting it to 0.05, the max number being 10, so only 10 people can fit in your elevator, and have the floor idle on 1. Click Submit and wait for the magic to happen.
Wow, look at that graph. Okay, now let's look at the output. On the x-axis, we have whatever variable we wanted to test. In this case, it's the number of elevators. On the y-axis, we have the average wait time as shown by the vertical box and whisker plots, which were generated from the average wait time of each experiment. With these plots, it's as simple as looking for the configuration with the lowest waiting time and choosing that configuration for your real system.
Thank you for your attention. If you have any further questions regarding the product or any individuals involved in the project, our contact information is provided here. Special thanks to Professor Richard Peters, who provided us with the necessary data to develop the program.